Hello, I am Dhilan Nanji, and this is Lab 4 Magnetic Braking with Faraday. Here are the contents of this report. Introduction. The purpose of this experiment is to determine the effects of Faraday's law and Lenz's law on the speed at which a bar magnet falls through a roll of aluminum foil and create a computational model to illustrate this interaction. Summary of the experiment. A bar magnet was dropped through a roll of aluminum foil north first, with the amount of time required for the magnet to fall through the tube being recorded. A computational model, which is explained later, was then used to calculate a theoretical value. The summary of the main results: the bar magnet took an average of 2.25 seconds to fall through the tube. The computed time was 0.233 seconds. The time it would take to fall the same distance through free space was 0.0782 seconds. Introduction. Key concepts and math models. Faraday's law, the relationship between the change in magnetic flux over time and the induced voltage, and it's the first equation shown. The Lenz's law, the induced current flows in a direction that opposes the change in magnetic flux. It's the diagram shown right under Faraday's law. Newton's second law, right under the diagram, the relationship between mass, acceleration, and net force. Kinematic Equations, relationship between time, velocity, position, and acceleration, is right below Newton's second law. Then the bottom two are the magnetic field of a dipole and magnetic force on a wire with a current, respectively. For this experiment, the initial conditions are shown below. The tube length is 0.302 meters, the width of the aluminum foil is 0.008 meters, the inner radius of the tube is 0.018 meters, the outer radius of the tube is 0.022 meters, the dipole moment of the bar magnet, mu, is 0.20028 from Lab 2. The system and surroundings: the system is the bar magnet, the surroundings are the aluminum foil roll, and everything else. This is a very straightforward experiment consisting of a simple procedure. For this experiment, a bar magnet was dropped through an aluminum foil roll. The time is recorded by taking a video of each trial and subtracting the time at which the magnet entered the tube from the time that it exited. Here's the data for the experiment. The magnet was dropped through the tube 5 times, and an average is taken of the amount of time it took for the magnet to fall through the tube. The average time was 2.25 seconds. Here are some excerpts from the code/computational model used in this lab. The first is a function using Faraday's law to find the change in magnetic flux over time through a ring or slice of the aluminum foil roll. Second is a function used in Lab 2 to calculate the magnetic field from a bar magnet or dipole, and it's reused for this lab. The third is Newton's second law relating the magnetic and gravitational forces, which also determines the direction of the acceleration of the bar magnet. The fourth is kinematic equations being used to determine the position and velocity of the bar magnet. The computational model gave a result of 0.233 seconds, significantly longer than the 0.0782 seconds calculated using the acceleration of gravity, length of the tube, and kinematic equations if the bar magnet were to fall through free space. This is also significantly less than the 2.25 seconds the magnet took to fall through the tube. The velocity versus time graph appears to be approximately linear while the magnet is in the tube. The red represents the counterclockwise current and the blue represents the clockwise current. The intensity of color represents the magnitude of the magnetic field shown on the bottom, and the graph is on the right. Discussion. Why can't we use a ferrous tube, for example a steel pipe? We cannot use a steel pipe or other ferrous materials since these materials can be magnetic through exposure to a magnet, and this may impact the results. What happens to the magnet? How is it compared to a magnet falling through free space without a tube? The magnet is slowed down by the magnetic force on it from the induced current in the foil. It falls significantly slower than it would through free space. The intensity of the coloring on the tube indicates the magnitude of current flowing through each ring. Red and blue indicate current flowing in opposite directions. Which color corresponds to which direction of current? How can you know? The red represents counterclockwise current and the blue represents clockwise current. This can be determined through Lenz's law. The current flows in the direction that maintains the magnetic field and resists the change in flux. What happens to the dynamics of the system when you flip the magnet around? Flipping the magnet around has no effect on the dynamics of the system. The magnetic field created due to Lenz's law will be the opposite direction, as the induced current will be the opposite direction, but the force will be the same. How does the total time in tube a real-world example compared to that of a computational system? How might the computational system be more accurate? The magnet was in the 2.25 seconds on average. The time given by the computational model was 0.233 seconds, a significantly smaller value. This is likely due to the computational model using a smaller dipole moment value for the magnet than its true value. The computational system may be made more accurate by using a more accurate value for the bar magnet's dipole moment. Increasing the number of intervals, decreasing dy, and the model will provide more data and increase accuracy. What does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? The velocity versus time graph is approximately linear while the magnet is in the tube, meaning that there was an approximately constant acceleration and therefore net force on the negative y direction. Since the net force and acceleration are downwards, the magnetic force is smaller in magnitude than the gravitational force on the bar magnet. The sources of error for this experiment include human error. Scrubbing through videos is often difficult to do precisely and may have led to times being somewhat inaccurate. I did attempt to verify this with a stopwatch, and that gave me slightly more accurate results, but there's still error present. In addition, the computational model may have been affected by an inaccurately measured mu value in Lab 2 for the bar magnet. It may have been too small. This may have contributed to the difference between the actual and theoretical values for the time magnet was in the tube. A higher mu, a center stronger magnet, would bring the theoretical value from the computational model closer to the actual value. If there was almost no resistivity in the wire, the induced current would increase until the magnetic field generated is enough to prevent the magnet from falling entirely. The gravitational and magnetic forces would also balance. If holes or slots were cut into the tube, there would be less material, essentially fewer loops, for the current to run through, leading to a weaker magnetic field from the induced current.